Hello everyone, I'm Amanda Murray, and for this research topic, I'll be talking about thunderstorm development in the High Plains. The reason why I chose this region is because I was actually stationed out there for 5 years. I'm from the East Coast and spent most of my life there, so when I got stationed out there, I thought the storms that developed, or rather the type of storms, were rather fascinating. As far as the area of interest goes, so the High Plains is an area extending from central Texas through the Panhandle up north to Nebraska, going from east to west. For my focus area for this project, though, it's going to be around the Caprock Escarpment, and that's annotated by the red rectangle on the map. Also, note that the Rocky Mountains are just to the west of the High Plains region, and that'll be important for future discussion here on the next few slides. So, how conducive is the environment? Oftentimes, the environment is not conducive for the development of thunderstorms, especially tornadic thunderstorms. In the High Plains region, it's noted that tornadoes are generally regarded as occurring relatively infrequently. There's a lot of reasons for this, and a lot of the different research has different ideas, such as higher elevation, how synoptic weather patterns interact with mesoscale patterns, topography, and how that interacts with large-scale moisture transport. Also, this area is very flat with a high elevation, and with the mountains just to the west, it's common knowledge that orographic lifting happens because of the mountains, and it helps initiate storm development. And also, with all of that being said, there have been instances where the environment was not conducive for the development of severe storms, but they developed anyways. All right, moving on to thunderstorm detection. So there are many ways to do this. I only have 3 listed here, but realize there's a lot more than just 3. These are ones that are pretty common though. Satellite images, like this one here to the right, is an IR satellite image with the really cold cloud tops being annotated in the bluish purple tones along with the white. Also, soundings and radiosondes. Satellite data is great because it provides a good indication of an indirect measure of conditional instability, meaning there is probably enough moisture and instability within the atmosphere for a parcel to reach the lifting condensation level and start rising to form clouds. Also, satellite imagery can help you identify shortwave troughs, which can help storm initiation. And of course, satellite data isn't the only thing that's used. It's used in conjunction with the soundings and radiosondes as well. Moving on to synoptic patterns. So in the High Plains region, weather systems generally tend to be weaker, and this may result in smaller scale systems to become significant because of an absence of strong, larger scale synoptic features. Also, the mountains in New Mexico, winds at the lower levels tend to be weaker with inflow from all directions, and as the air goes over the mountains, it experiences a series of strong updrafts and downdrafts with a net weaker upward ascension. So this can help create storms, but overall it's generally regarded to be weaker versus the synoptic patterns over in Tornado Alley, for example. Rockwood and Maddox studied one particular storm that initially came from fairly weak synoptic conditions, which were unfavorable for storm development. Initially, Dreyer had moved behind a weak trough located in this region with a weakening cold front. The atmosphere was minimally stable. There was a weak shortwave trough and weak warm air advection, along with a capped area which prevented some of the convection. However, a derecho still developed. They also noted that there was a presence of a low-level jet streak. So that may have been another factor which was very conducive for storm development. Moore in 2003 found that the presence of a low-level jet helped sustain the elevated storm structure. And for these elevated storms, they are often found above frontal surfaces, and they're isolated from diabatic effects, which are necessary for storm development. Moving on to mesoscale patterns, so there's a lot of smaller scale patterns which can help or hinder storm development. Strong low-level convergence, presence of a weak dry line. It's generally weaker in this area, and along with outflow from other storms. One particular storm that Rockwood and Maddox found, it developed over a weak dry line, and they also noted that this area may have had the strongest low-level convergence. Raymond and Wilkening found that vertical mixing, which is a process which a cloud has inflow from its top and bottom along with net outflow on all sides, is important for how clouds form. Doswell in 2002 looked at a storm which formed near the dry line in eastern New Mexico as it propagated eastward. As it moved into an area of increasing stability which consisted of cloudy, relatively cool air, resulting in the storm becoming elevated. Also, dry lines can be hard to predict, but deep convection can form along dry lines, which could lead to development of severe thunderstorms. So if we take a look at this map, for example, which points out the dry line here, it's really hard to see in this picture. However, there's two areas circled in yellow. The one to the east has a temperature of 79 and a dew point of 67. So the dew point temperature spread isn't very large. It's indicating it's very moist air. And then the one just to the west has a temperature of 85, but its dew point is 11. So that's very, very dry air. As far as the data that I acquired, I looked at April through June of 2015 in particular. And this time frame was chosen because it's relatively recent and because springtime tends to have more convective initiation than the rest of the year. Obviously, storms can develop in the rest of the year, but springtime is when you're going to find the most storms. I collected soundings from Amarillo and Midland, Texas. I wanted to grab some from Albuquerque, but the websites that I looked at did not have these soundings available from Albuquerque in their archives, so I'm limited to just these two for now, unless I can find more as I continue to look at everything here. I also collected convective outlooks for this time frame, storm reports, and any associated watches and warnings. I also limited myself to 1 year only, just so simply I wouldn't be overwhelmed with too much data. However, it'll be even better if I include multiple years, and that's something that I can always look at in the future. All right, for my hypothesis, for my null, I have days that are predicted to have severe storms will always develop storms, and for my alternate, severe storms develop regardless of favorable conditions, meaning storms may develop even if the conditions are not favorable. Going to the methodology, so like I said, I acquired SKUTs from Midland and Amarillo, Texas, and I put everything in a spreadsheet. So I had all the days listed, and I marked which stations I pulled SKUTs from, and as far as which SKUTs I decided to pull from, I looked at ones that were favorable for storm development by looking at total totals, lifted index, and CAPE. And in general, I picked ones that had at least a few hundred joules per kilogram of CAPE. I also marked which days had convective outlooks, watches, and next to them. And I also marked which days had storms. And what I found was actually pretty interesting. So as far as my results go, I have a graph here. Storm development without issued convective outlooks and or watches. I have number of storm days listed on the y-axis, and then I have the storm type listed on the x-axis down below. For the ones without issued convective outlooks and or watches, and 6 storms that developed hail, 6 that produced wind only, 3 that produced wind only, 1 that produced hail and wind, and then 4 days that produced tornadoes. And please remember that it's not 4 storms that produced tornadoes. It's meaning that there was 4 days within this 3-month time period that formed tornadoes. There may have been 5 or 6 tornadoes on one particular day, so just keep that in mind. So more storms actually developed on days that did not have an associated convective outlook or watch with them. And of these storms, as you can see on this graph, most were not tornadic either. However, there was an equal number of tornado days for each scenario. So for the next scenario here, I have storm development with issued convective outlooks and or watches. So I had 3 days that had storms which produced hail, none that produced wind, and 2 days that had storms that produced both hail and wind, and like I said, 4 that produced tornadoes. And please remember, it's number of days, not number of storms. All right, for the skew-T comparisons, I got the number of days listed on the left again. And then I have 3 groups here. I got favorable conditions for storms, and that's just based on the skew-Ts that I had collected. And I did this for Amarillo, Midland, and I have one combining both stations. And as far as the number of storm days, there was roughly a month or so that had storms produced on this. And then as far as storms with the watch or a convective outlook, probably should have put convective outlook on there instead of watch. Anyways, there was a lot less storms that produced versus days where storms were produced without a watch for each station. And there were multiple days with favorable conditions for storm development. However, like I said, no development was initiated on most days, and there was a higher number of storm days without an associated watch or convective outlook. Also, I plan on looking at synoptic and mesoscale conditions to see why this occurred, and I'll take a deeper dive into the skew-Ts to look at the lifted condensation levels as well.